Let me put on the recording. Good morning. So we recollect today some of the topics that we have examined. Last week, you may remember that we were discussing the superposition principle. So we were considering the case of a situation in which the problem we are considering is conservative, but on the other hand, the total energy is not known. So we are using the most general form of the wave function that is a superposition of monochromatic components. And we have also given a name to this superposition. We call it a wave packet. That is the same name that is given in the electromagnetic theory to the analogous construction made of the superposition of electromagnetic waves. Again, I remind you that the wave function is not electromagnetic, it is a probability density. From the practical standpoint, the use of a wave packet is useful because by suitably combining the coefficients of the superposition, we can construct a wave packet that is essentially non-zero in a limited region of space and goes to zero outside this region. So in this way, we are able to recover, in some sense, the localization of the particle. We may assume that the particle stays in the region of space in which the localization probability is non-zero and does not stay in the remaining parts of the space. Obviously, in general, the wave packet moves in space, so the position of the center of the wave packet changes with time. These concepts are very useful because they allow us to reconstruct the dynamics of the wave packet that is similar in some sense to the dynamics by which we describe a particle in classical dynamics. So I'm going to share the screen. Oops. You should be able to see a slide entitled Wave Packet 1. When we construct the wave packet as a superposition, we must use the ingredients that are available to us. So for instance, if we have found the solution of the Schrödinger equation independent of time by solving a problem whose eigenvalues are discrete, then we shall find a superposition in which the monochromatic waves are combined in a sum, as you can see in the first line of the screen. The wave function is given by the sum of monochromatic terms in which we have Wn and E sub n, that are the eigenfunction and the eigenvalue of the Schrödinger equation independent of time, and each monochromatic term is multiplied by some coefficient C sub n. And you remember that we are able to find the coefficients provided we know the initial condition. On the other hand, it may happen that the Schrödinger equation independent of time provides us with a continuous spectrum of eigenvalues. In that case, instead of using a sum, we must use an integral, as visible in the second line of the screen. So in that case, we have still the exponential of minus E sub k, but k, E, the eigenvalue, or E sub k is a continuous variable. So k also is a continuous variable. So we have to integrate over the continuous parameters k that are 3 because we are in a 3-dimensional problem. You remember that there could be a third possibility, that is a mixed spectrum. We shall never use this case, but keep in mind that it could exist. Now we want to see how it is possible to provide an approximate description of the wave packet. The two expressions that you see are fully general. One applies in the case of discrete eigenvalues, the other applies in the case of continuous eigenvalues. Okay? We can give an approximate form by assuming that the wave packet has some properties. We give an example, a very easy example. The example is that of a free particle. And when we consider a free particle, you remember, the eigenvalues are continuous. We have solved the case of the free particle in one dimension. And you remember that in one dimension, the relation between the k vector, the wave vector k, and the energy is that the energy is h bar squared over 2m times the square of the wave vector. This is in one dimension. In 3 dimensions, it is the same, because the Schrödinger equation for a free particle is very easily separated. Okay, so we solve in 1 dimension at a time, and then we put the 3 solutions together. We shall see it in details later on, but for the moment, just accept that in 3 dimensions and for a free particle, the eigenvalue E sub k is simply h bar squared over 2m times the square modulus of the wave vector. So that is k1 squared plus k2 squared plus k3 squared. And the eigenfunction, you remember, in the one-dimensional case, the eigenfunction is exponential of j kx divided by the square root of 2 pi. In 3 dimensions, it is just the product of 3 similar functions, so it becomes exponential of j k dot r, scalar product of the wave vector times the position vector. And then we have the factor 1 over the square root of 2 pi 3 times, so it becomes 1 over 2 pi to the 3/2. The notation that we are using here is such that the components of k can be either positive or negative. So each component, ki, goes continuously from minus infinity to plus infinity. You can note that for each value of energy, there is a triple infinity of possible components, K1, K2, K3, such that the expression of the energy in terms of the wave vector applies, because the expression of E sub k as proportional to K1 squared plus K2 squared plus K3 squared is essentially the equation of a sphere in the three-dimensional space of vector k. That means that there are infinite possible directions of the radius so that we obtain the same energy, because for the energy it suffices to prescribe the modulus of the radius. So this is a very easy case in which we notice that the order of degeneracy is infinity to the third, because for one given value of energy, we have infinity to the third possible k vectors that corresponds to infinity to the third possible eigenfunctions. Now, we change the notation as usual, so that is, we impose, or we adopt the symbol omega, the angular frequency that is E of k over h bar. And then we manipulate the wave packet. We assume that there is a peak in the wave packet that corresponds to some value k0. Okay? So that there is some k0 to which there corresponds a maximum of the wave packet. And then we approximate the wave packet around that zero. And this is easily done because you see that the angular frequency is proportional to energy, and energy is proportional to the square of k. So for each component, we manipulate the square of k by adding and subtracting the corresponding component of the vector k0. And then we expand the quadratic form. So we have ki squared is equal to k0I squared plus, then there is a term that is first order in the difference ki minus k0I, and then we have a term that is second order. If we replicate this construction for each component, we can express omega as you can see in the central line of the page. This is no approximation. This is simply another possible way of writing omega such that we have this important vector k0 appearing in it. Okay, k0 corresponds to the maximum of the wave packet in the k space. Okay, so we have omega equal to a constant plus a linear term in the difference k minus k0 plus a quadratic term again in the difference k minus k0. I remind you that the coefficients of the expansion are found by considering the wave function at time equal to 0, and then taking the scalar products of the eigenfunctions w times the wave function. So in this particular case, of the free particle in the continuous situation, then we find easily that the coefficients are exactly the Fourier transform of the wave function at the time t equal to 0. So far, we did not introduce any approximation, okay? Next, we are going to introduce an approximation that consists in neglecting the quadratic term in the expression of omega. So we say, if we have good reasons to assume that the only values of k that are important are those in the vicinity of k0, then the difference k minus k0 will be small, and by this reason the difference of k minus k0 squared is even smaller. So we shall neglect the square, the term of the second order in the expression of omega. So the idea is, assume that the width of the Fourier transform is small, so that the function c of k is a function in the proper meaning of the term, because k is a continuous variable. We assume that the function c of k has a peak corresponding to k0, and that when we go away from the peak in the k space, the wave packet becomes negligible. If that happens, as we said before, the only values of k that are of any importance for the wave packet are those that are in the vicinity of k0. So we neglect the quadratic term in omega, and we introduce a simplifying definition, because you see that in the expression of omega, the coefficients of the first order term is h bar k0 divided by m. But you remember that for a free particle, h bar k0, or in general h bar times k, is the momentum, okay? So h bar k0 has the units of a momentum, and when you divide it by the mass, you obtain a velocity. So the quantity h bar k0 divided by m is a velocity. And also the term of zero order has the same units as omega. So h bar k0 squared over 2m is a quantity with the units of omega. So we introduce the definitions. Omega 0 is defined as h bar over 2m k0 squared. And we call UG the quantity h bar k0 over m. UG is also called the group velocity, and you may have already met the concept of group velocity in the electromagnetic theory, because it is the velocity of the wave packet in the electromagnetic theory. Okay. For this reason, we call it U sub G. Now remember that omega appears in the exponent inside the integral. You remember E sub k over h bar is omega. So what we are doing essentially is that we approximate the exponent inside the integral. And this exponent is imaginary because we have minus j times a real quantity, okay? So the validity of the approximation must be discussed by considering what happens if we approximate the exponent in the imaginary exponent of a formula of this form. Obviously, the maximum elongation of this exponent is 2 pi, okay? Because when we have an imaginary exponent, the exponential takes again its value after a rotation by 2 pi of the exponent itself. So the validity of the approximation applies if the term that we neglect is small with respect to 2 pi. Okay, why should we care about this? Because inside the exponent there is also the time, and the time evolves. So this t inside the exponent is continuously growing, okay? So since it multiplies everything in the exponent, it multiplies also the term that is being neglected, okay? So it is necessary that we carefully apply the approximation only for the duration of time during which globally the term that is neglected is negligible with respect to 2 pi. So the approximation is legitimate. It is written here. If the quadratic part h bar k minus k0 squared times t divided by 2m is smaller than 2 pi, okay? So assume that we are in these conditions so that we consider the wave packet for a relatively short interval of time. And then we put together all the constants, okay? Clearly, in the phase, we have some terms that are constant. For instance, we have a term that is equal to k0 dot r minus omega 0 t, because when we replace the expression of omega in the integral, we have omega 0. Omega 0 here does not depend on k anymore because it is a constant. So the part of the exponent that depends on omega 0 can be taken out of the integral. But you may imagine also that in the space part of the wave function, we also replace k with k minus k0 plus k0 in order to have the difference k minus k0 visible. By this doing, we also have a term that is of the form jk0 dot r that does not depend anymore on the integration variable. So we can extract this jk0 r from the integral. Okay, so we can clean it up a little bit. So we take out k0 dot r minus omega 0 t, and we call it globally phi 0. This is a phase that depends only on r and t and parameters, okay? So the wave function essentially after this approximation has a factor that is the exponential of j phi 0. And what is left inside the integral is a simplified form in which we have c of k divided by 2 pi 3/2, the exponential of j, and then we have a parenthesis r minus ugt dot k minus k0, all of this integrated over over k. Now you observe that the integral, of course, the integral does not depend anymore on k because k is saturated. It will depend on k0, and this k0 is fixed, okay, because we are considering the center of the wave packet. And then it will also depend on an argument that is r minus ug dot t. This argument does not contain k, okay? So when we calculate the integral, this argument will be untouched. So globally, if we give a simplifying form or simple name to the integral, we call it capital A. This capital A essentially depends on r minus ugt and on k0. And we call this the envelope function, okay? In conclusion, after these simplifications, the wave packet has a form given by the product of the envelope function A, you can see it in the last line of the page, times the exponential of j phi 0, okay? But you remember that the localization of the particle is given only by the square modulus of the wave function, not by the wave function itself. So when we take the square modulus, obviously the square modulus of the exponential of j phi 0 is equal to 1, so it does not contribute to the localization. And what is left is that the square modulus of the wave function is equal to the square modulus of the envelope function. So the envelope function contains the total information about the localization of the particle. Obviously, the envelope function moves in space as the original wave packet was doing, okay? So how is the motion of the envelope function in space? Well, the envelope function depends on an argument that is r minus ugt. And you remember from elementary physics that if you have a function that depends on position and space in this form, then this function moves rigidly with the velocity ug. So the envelope function moves rigidly. That means that it is not deformed. It moves without any deformation in space with the velocity equal to ug. This is the reason why we call ug the group velocity, because it is the velocity of the envelope, and the envelope does not deform, okay? Obviously, this is an approximation that applies only as long as we can neglect the quadratic term in the angular frequency, okay? Some of you may remember that we used the same concept of wave packet in the electromagnetic theory, but the electromagnetic theory is simpler if you consider the propagation of radiation in vacuum, okay? Why is it simpler? Because you remember that in the electromagnetic theory, the angular frequency is simply proportional to the modulus of the k vector, okay? So omega is linear with respect to k. It is not quadratic. So there is no need whatsoever to simplify anything. The electromagnetic theory, it is just simplified by itself because it is linear. So a wave packet constructed using electromagnetic waves propagates in vacuum without any deformation forever, because each monochromatic component propagates with the same speed, that is the velocity of light, the speed of light in vacuum. Okay. So for the electromagnetic wave packets, there is no deformation in vacuum. If they propagate within a medium, they do deform because you remember the phase velocity depends on the frequency. Also for the electromagnetic field, okay? So coming back to the wave packet, we have this picture. Why is it useful? Because essentially we can ascribe a velocity to the wave packet as if the wave packet was a particle. We can ascribe a momentum by considering that the momentum is the momentum associated to K0, the central point of the wave packet in the K space. But we can also ascribe a position because the wave packet is also limited in the physical space. You remember that the norm of the Fourier transform is equal to the norm of the function. So also, if the wave packet in the K space has a finite norm, it will have a finite norm also in the position space. So we can define a center of the wave packet also in the position space and think of it as the position of the particle. Okay. So slowly we can recover this concept of position and momentum, although with some approximation, also in the quantum mechanical description of the motion of the particle. Besides, we use the same concept also in crystals, because due to periodicity of the crystals, with some longer manipulation, we can again mimic the propagation of the wave function inside the crystal, the wave function describing an electron, for instance, as a wave packet with limited size in the physical space and also with the limited size in the momentum space. So again, we have a description of the motion of the particle that is similar, in quotes, to the classical one. In general, when we want to describe a particle with a wave packet, we try to use a Gaussian wave packet because the Gaussian wave packet has some properties. That one property is something that we shall see later, is the so-called minimum uncertainty wave packet. It is the form of the wave packet in which at the same time the extension of the packet in the physical space and in the K space are the narrowest together. So the Gaussian wave packets are very convenient. So qualitatively, assume that the function that is visible in the upper left part of the figure is some exponential of jkx. It is not, because it is written sine of 10x, so it is a sine. It's just one of the two parts of the complex exponential. Anyhow, that is an oscillatory function, okay? With a period that is not extremely high, okay, 10, but yet you see that, sorry, frequency, but practically such a function is not able to provide you with any information whatsoever about the position of anything, okay, because it oscillates in the same way everywhere in space. Then assume that you attach to it an envelope function of the Gaussian type that you see in the upper right part of the figure. You see that it is exponential of minus x squared over 50, okay? So you have an oscillation and you have an envelope. Now, if you try to multiply the two functions, obviously what you find is the function that is visible in the lower left part of the figure. It is the product of the oscillatory function that you see above and the envelope function. At this point, you may already distinguish that this product is able to provide you with some information about the position of the particle. Finally, you take the square modulus. Actually, you take the square because these are real functions, okay? So if you take the square, you have a function that has a peak at some position and then decays on the sides. So this function is able somehow to provide you with the information about the localization of the particle. And this is the product, the squared product of the original oscillatory function and the envelope function. Obviously, the oscillatory part still exists, but does not provide you with any form of information, okay? Why do you see the oscillatory part? Because here we have used the sine function and not the complex exponential. The complex exponential would give you 1 and that's it, okay? Here we have used real functions, so you still see the oscillatory part. Okay, so far we have considered only one possible equation in quantum mechanics, that is the Schrödinger equation. The Schrödinger equation is built up with the Hamiltonian operator, and you remember that the Hamiltonian operator is the quantum counterpart of the Hamiltonian function of classical mechanics, and the Hamiltonian function is correlated with the energy of the particle. In fact, the solution of the Schrödinger equation provides you with the eigenvalues of the energy and the eigenfunctions associated to the energy. The question is, in mechanics, we have many other dynamic properties, position, momentum, angular momentum, etc. Okay? So what should we do if we want to investigate the other dynamic properties? What we do is just that we extend the concept that we have considered for the Schrödinger equation, okay? And we do it by stating a number of postulates. And these postulates work because the experience showed that they are consistent with reality. Okay, so they are applicable to the practical cases. So we shall now see these postulates. that go under the name of postulates of quantum mechanics, or also general methods of quantum mechanics. For them, what we do is essentially a generalization of the concepts and conclusions that we have reached so far for the energy. Okay. So you remember that one of the conclusions that we found was that the only values allowed for the energy of a particle subjected to a conservative force are the eigenvalues of the time-independent equation, that is the Schrödinger equation. Hamiltonian applied to W equal to the eigenvalue multiplied by W. And how do we derive the Hamiltonian operator from the classical Hamiltonian? We replace each component of momentum, Pi, with an operator that we call the momentum operator, that is minus JH bar derivative with respect to the coordinate, with the space coordinate of the same index I as the momentum. Then, assuming as usual that after solving the Schrödinger equation, we have found a discrete set of eigenvalues, we construct the wave function by a superposition. We are still in the conservative case. And this superposition has coefficients that are found from the initial condition. We know that by definition, the localization of the particle is provided by the square modulus of the wave function, that is the probability density. Of course, we assume that this wave packet is normalizable. So the square modulus of psi is the probability density of localization of the particle. And we also observed that if we measure energy, then we find one of the possible eigenvalues that is equivalent to setting all coefficients Cn to 0 but 1, the one that corresponds to the eigenvalue of energy that we have found by measuring. Then the time evolution of the wave function is given by the time-dependent Schrödinger equation JH bar derivative of psi with respect to time equal to the Hamiltonian applied to psi. This is true also in the non-conservative case. Okay? In the conservative case, this equation is already implied by the expression of the superposition principle. Of course, there are issues that are still open. So, how can we calculate the probability when we measure energy that the measurement of energy will be some eigenvalue? But the hypothesis that was already done, you remember, was to associate this probability to the square modulus of the coefficient. And the reason is that by Parseval's theorem, you remember, the sum of the square moduli of the coefficients is equal to 1. So all the coefficients are terms such that the squared modulus is a non-negative number such that the total is equal to 1. So they may be thought of as probabilities. And we also understood that if we do measure energy and we find one eigenvalue, then we have the certainty. Okay, so the certainty implies that the coefficient of that eigenvalue becomes equal to 1 and all the remaining coefficients are equal to 0. Okay, so it is sensible to relate the probability to find an eigenvalue of energy to the square modulus of the corresponding coefficient in the expansion of the wave function. The question is how do we calculate the probability to find the value of any other dynamical quantity, like momentum or angular momentum, capital M? And the answer is we proceed by analogy. Proceed by analogy means that we have to replicate this page for any other dynamical quantity. That is, we postulate that for any dynamical quantity of interest, we must construct an eigenvalue equation. Then the solutions of the eigenvalue equation, that is the eigenvalues, are the possible values taken by the quantity of interest. And the eigenfunctions form a complete set, such that if we wish, we may expand the wave function in terms of the eigenfunctions of this new operator for this dynamical quantity. If we construct the description of the wave function in terms of these eigenfunctions, there will be coefficients in the expansion. And the postulate goes that the square modulus of the coefficients will give us the probability that a measurement of the dynamical quantity of interest is one of the eigenvalues of the quantity itself. The final question is, how do we find the form of the eigenvalue equation? Because in order to find the eigenvalue equation, we need an operator. And the answer is we proceed in the same way as we did for the Hamiltonian. We start with the classical expression of the dynamical quantity, and then we look whether in this expression there are the components of momentum. So we have to write it in terms of, in general, momentum and position coordinates. The position coordinates are left untouched. We don't modify them. The components of momentum must be replaced with the momentum operators, just in the same way as we did for the Hamiltonian operator, okay? Then there is a tricky part, because you remember the outcomes of a measurement are the eigenvalues, but for this to be possible, the eigenvalues must be real. Otherwise, we don't get anything of interest. But the eigenvalues are real only if the operator is Hermitian, okay? So when we construct the operator, then we have to check whether the operator is Hermitian or not. If it is not Hermitian, we cannot accept it. We have to change something, okay? But now it is 10. So we stop for 10 minutes and we shall continue on this line in 10 minutes. Okay, so let's continue. You should be able to see a screen with the indication postulates of quantum mechanics. And we now list the postulates by repeating substantially what was said in the previous, in the end of the previous hour. So we start from a general physical quantity, A. It could be energy, momentum, angular momentum, position, anything. And we associate an operator to the physical quantity. When we have a physical quantity of classical mechanics to which we have associated an operator of quantum mechanics, we call this observable. So an observable is a physical quantity to which an operator is associated. How do we construct the operator? First, we express A in terms of the so-called canonical coordinates. The canonical coordinates are position and momentum coordinates. Position and momentum. Then we leave the position coordinates untouched, and we replace the components of the classical momentum with the components of the momentum operator, minus j h bar, derivative with respect to qi. We use the symbol qi because in the theory, in the formal theory of classical mechanics, Q is a more general symbol to denote the coordinates, because if we denote the coordinates by x, y, and z, or by the vector r, we imply that we are using the Cartesian coordinates. But for instance, we may choose to use the spherical coordinates, okay? That are different from x, y, and z, but yet they are good coordinates anyhow. So in classical mechanics, one uses a more general symbol to denote any set of position coordinates that we want to use, and this symbol is Q. Obviously, if we are not using the Cartesian coordinates, then the components of momentum are not the usual components of momentum, as in a conservative case is the product of mass times velocity. They are other components that are the so-called canonally conjugate components to the Q coordinates. We don't consider this, okay? When we shall use some example, we shall always consider the Cartesian coordinates, okay? But this was just to explain why sometimes the components of position are indicated with the symbol Q. So we construct the momentum operator, and then after constructing the momentum operator, we use this in the expression of the observable A in order to form the operator A associated to it. At this stage, we shall check whether the operator is Hermitian or not. If it is Hermitian, we keep it. If it is not, we have to discard it and we reconstruct the operator better in order to achieve an operator that is Hermitian. The next step is that using the operator A, we form the eigenvalue equation. The eigenvalue equation, of course, is written A applied to some function that we call V is equal to the eigenvalue A times V. After solving the eigenvalue equation, we have a set of eigenfunctions. We must check whether the set of eigenfunctions is orthogonal and complete. Okay? This is a task that for the standard situations typical of quantum mechanics, the mathematicians have already performed this job for us, so we know that the eigenfunctions of the operators that we typically use are form a complete and orthogonal set. When we solve the eigenvalue equation, we must impose boundary condition because this is a typical equation in space, in the space coordinates. Okay. So the boundary conditions are the same as those that we apply to the Hamiltonian case. That is, the eigenfunctions must vanish at infinity. At this point, we can exploit the completeness of the set of eigenfunctions. And you remember, completeness means that we are able to expand a function in terms of the complete set. The complete set has the eigenfunctions that depend on position. So if we want to expand the wave function, the wave function, you remember, depends on position and time. So if we expand the wave function in a set of eigenfunctions that depend only on position, then the coefficients, of course, will depend on time. This is just the same as we found for the Hamiltonian. Okay, in the Hamiltonian case, you remember the eigenfunctions are called W, and in the expansion we have the time terms that are the monochromatic terms associated to the eigenvalues of energy. Okay. In the case of another operator that is not the Hamiltonian, we don't know what the form of the time components is. Okay, so if we have a discrete set of eigenfunctions of A, as you can see in the left part of the equation, then the expansion of the eigenfunction will have the form of a sum over n of some coefficients an that depend on time, each multiplied by the corresponding eigenfunction Vn that depends on position of the operator A. If conversely, the eigenvalue equation provides a continuous set of eigenvalues depending on some parameter beta, then the expansion of the wave function in terms of the eigenfunctions will be an integral over beta, in which the coefficients are some A beta that depend on time times the eigenfunctions V that depends on position with parameter beta. Okay, so n and beta are either discrete or continuous indices. Okay. Then, according to the rules, what is the form of the coefficients? The coefficients, as you remember, are obtained as the scalar products of the corresponding eigenfunction Vn or V beta times the wave function. This is, as usual, the expression of the coefficients. If also if the wave function is normalizable, then its norm is equal to 1, and due to the Parseval theorem that you remember, also the norm of the coefficients will have the property that in the discrete case the sum of the squares of the coefficients is equal to 1. In the continuous case, the integral of the squares of the coefficient again will be equal to 1. Okay, so we assume that the normalization condition applies, so we have this property for the coefficients. Okay, at this point we may exploit the coefficients to find the probability that a measurement finds one or the other of the eigenvalues of the operator A. We start with the discrete case because it is simpler. So the postulates continue by assuming that the eigenvalues of the operator A, that is A sub n if we find a discrete situation, or A sub alpha in the continuous case, are the only values that the measure of the physical quantity A can find. Then, if the wave function is normalizable, in the discrete case, the postulate goes that a measurement of A has a probability to find the eigenvalue of index n, A sub n. The probability is the square modulus of the corresponding coefficient in the expansion. So an square modulus is the probability that we may call P sub n, that a measurement of the physical quantity A finds eigenvalue A sub n in the discrete case. In the continuous case, the situation is a little bit more involved because you remember the normalization condition tells you that the integral of the square modulus of A beta is equal to 1. So this is a number. That means that the quantity modulus of A beta squared times the differential d beta is a pure number, is an infinitesimal quantity that is a pure number. Okay, so this product A beta squared times the differential is an infinitesimal probability, which is obvious because we have to integrate over the domain of beta in order to find the normalization. So in the continuous case, we must define an infinitesimal probability, square modulus of A times the differential d beta, and this is the infinitesimal probability that the measurement provides an eigenvalue that is in the interval d beta around beta. So this is an infinitesimal probability, okay, which also implies that the modulus of A beta by its squared by itself is a probability density, okay, because beta may have units, okay, or in general it does have units, okay. So this is the set of postulates that show how to construct the operator, how to form the eigenvalue equation, how to expand the wave function, and how to give a meaning to the coefficients. We anticipated that since the eigenvalues must be real because they represent a physical quantity, then the operator must be Hermitian, okay? You remember that an operator is, if an operator is Hermitian, then the eigenvalues are real, and we can also demonstrate the inverse property, that is, if the eigenvalues are real, then the operator is Hermitian. That is the reason why you see if with two Fs. It means if and only if, okay? The eigenvalues are real if and only if the operator is Hermitian, okay? We must check this property on a case-by-case basis, okay? You have an example here. Take a very, very simple observable, okay? That is x times px, that is the coordinate x in Cartesian components multiplied by the component of momentum along the x-axis, x, px, okay? Of course, in classical mechanics, x and p commute. You may take the product by placing x to the left, or you may place x to the right of p, okay? Or you can also use a fancy expression in which you take xp plus px divided by 2, okay? This looks strange, okay, because of course it is equal to the other ones, but it is just another possibility to write the product, okay? Now, if we start from any of these three possible expressions of the product, and we construct the corresponding operator, in the first case, we have x on the left, then, well, minus j, h bar are constants, so we can place them where we like. And then we have the derivative with respect to x, that is the momentum operator. Okay, so we have x followed by the derivative with respect to x. Of course, this derivative operates, being an operator, operates on every function that is placed on the right of it. The second case is p followed by x. So in this case, we have the derivative followed by x. So if we place another function on the right, then we must take the derivative of x times the function. So this is different from the other one, okay? Also, you may check to see whether any of these two forms, the first or the second form, are Hermitian, and none of them is Hermitian, okay? So these two operators should be discarded. They are not Hermitian, okay? Instead, if you take the fancy form, that is the symmetrized product, xp plus px divided by 2, you find the operator minus jh bar divided by 2 times x derivative plus derivative x. And you find easily that this is Hermitian. So the fancy form, that is the symmetric one, is the correct one. That is the one that must be chosen to form the Hermitian operator. This is generalized, but this page is not very important. It is generalized because if you instead of taking x, you take any function of x, and you do the same, any function followed by p, or p followed by any function of x alone, or the symmetrized form. Also, in this more general case, you find that the symmetrized form is the only one that works, okay? This is useful because in the discretization, in the quantization of the dynamics of a particle, of the charged particle subjected to the electromagnetic field, what you find is exactly this type of product, okay? But we shall not consider this case. So. Okay. Another issue is that apart from being Hermitian, the other thing that is necessary is that the set of eigenfunctions that are associated to the operator is complete. And this also, as I said before, must be checked on a case-by-case basis, but this has been checked already by the mathematicians, okay? We already showed a demonstration that if an operator is Hermitian, then the eigenvalues are real, okay? We have seen this a few hours ago, I remember, okay? There is also the converse theorem. If the eigenfunctions form a complete set, okay, then an operator having real eigenvalues is Hermitian. So also the converse of the theorem is true. We don't go through the demonstration. And now we consider another very important issue. This important issue is the issue of the so-called separability of the operators. Separability is important because if an operator is separable, in general, it is much easier to solve the eigenvalue equation because we can do it one coordinate at a time, okay? So let's consider this rather general case. We consider an operator A that acts only on the coordinate x. What does it mean? That if there are derivatives, for instance, the derivatives inside the operator are only with respect to the x coordinate. Then consider a second operator, B, that acts only on the y coordinate, and another operator, C, that acts only on the z coordinate, okay? So for each of these operators, we can set up an eigenvalue equation. So A contains only x. So we form an eigenvalue equation visible on the left of the equation. A applied to u k equal to a k, that is the eigenvalue times uk, in which A acts only on x, so it contains only the x coordinate, and similarly u contains only the x coordinate. In parallel, we built up the eigenvalue equation for B, and this depends, the eigenfunctions V depend only on Y. And finally, we built up a third eigenvalue equation, this time for C, and the eigenfunction W will depend only on Z, okay? we are using, as usual, the discrete spectrum because the notation is simpler. And we also assume that the set of eigenfunctions U is complete, of course, with respect to X. V is complete and W is also complete. Okay. Now let's see whether we succeed in expanding using the set of eigenfunctions U, V, and W. We want to expand a general function f that depends on all coordinates. Okay. We can do it step by step because we may, for instance, try to expand the function f in terms of the w's. Okay, so the w's depend only on z. When we do so, you remember the coefficients of this expansion that we call a sub n are obtained as the scalar products of w times f. So by construction, these coefficients will depend on x and y. Okay. At this point, we view a sub n as a function of x and y, and we expand a in terms of the v eigenfunctions. So we expand it with respect to the dependence on y. And the result is in the brackets of the same line, okay? We see that a sub n can be expanded as a sum over an index m of some coefficients b times vm. But these coefficients are obtained by considering the scalar products of a times v. So of course they inherit the dependence on x, but also they inherit the dependence on n. So the coefficients will have two indices, bm because we are summing up over m, and n because it comes from the an function that is being expanded. Okay. Obviously, the last step is obvious. Okay. We expand bmn in terms of the uk functions. Okay, so we obtain coefficients that will be called ckmn. Okay, so the conclusion is that indeed, if we have the eigenvalues of operators that operate only on x, y, and z, we can expand any function f as a triple expansion in which we are using the products uk, vm, wn. Okay, but there is more. Let's see what happens if this function f is a solution of an eigenvalue equation. We can even generalize the concept a little bit more. And consider an operator that is a linear combination of the three original operators, A, B, and C, in which the coefficients are vectors, are constant vectors, A, B, and C. Okay, so we take any constant vectors, small a, small b, and small c, and we construct a linear combination of the original operators using this vector. In this way, we construct a vector operation, a vector operator AA plus BB plus CC, okay? And this vector operator operates on X, Y, and Z, but it operates separately because it is made of 3 blocks. The first block contains only the operator A, so it acts only on X. The second block acts only on B, and the third block acts only on C. If we apply this operator on the individual term UK, VM, Wn of the expansion of F, okay, it is immediately seen that the result will be the vector A times the eigenvalue AK plus B Bm plus CCn times the same function, okay? So we can obtain this result simply by going back to the original eigenvalue equations that are present in the first line of this page and simply replace them in this equation, okay? So this relation at the bottom of the page is true. But you see immediately that this is an eigenvalue equation in which on the left we have the quantity in parentheses that is an operator. The product UVW is the eigenfunction. The quantity in parentheses on the right is the eigenvalue, that in this case is a vector, times again the eigenfunction. Okay, so you see that it is a very important result because you see that when an operator is separable, that is, it can be written as the sum of blocks, and each block depends only on one coordinate, okay? Then the eigenvalue is the sum of the individual eigenvalues. Is the sum of a piece that contains only AK, another piece BM, and another piece CN. And the eigenfunction is the product of the individual eigenfunction. So this is a fundamental property and very useful from the practical viewpoint. When an operator is separable, the eigenvalue is the sum of the individual eigenvalues of each individual piece of the operator, and the eigenfunction is the product of the individual eigenfunction. Keep this in mind because we shall use this on other occasions. Let's consider two important examples. We want to consider position. So we have to apply the procedure that we have described so far to the position. The position is a possible observable, of course, in mechanics. So we start with the standard definition of position of classical mechanics, that is R. R is a vector of components x1, x2, x3, and the individual I1, I2, I3 are the unit vectors of the coordinate axis. So you see immediately that R is a quantity that is intrinsically separated into 3 pieces. Each piece depends only on one and only one coordinate, okay? And it is a vector. You remember that the general postulates of quantum mechanics prescribe that when we construct an operator starting from the classical expression of the dynamical quantity, the position coordinates must be left untouched. So when we transform the position into an operator, the position just remains the same quantity. There is nothing to change. Okay, so position stays the same. Then we construct an eigenvalue equation with position. So we have to consider R as an operator, but it is a very simple type of operator because it is a multiplicative operator only. Okay, so R multiplies the eigenfunction that we call f, okay? And the result must be the eigenvalue that we call R0 because we must use a different symbol times fr, okay? Of course, we can split this into 3 blocks. You remember when we have an operator that is the sum of blocks, each block acting on a single coordinate, the eigenvalue will be the sum of the eigenvalues and the eigenfunctions would be the product, okay? So we consider the individual component and we construct the eigenvalue equation for the individual component. So in this line, you can see that the component of index I of position is xi, the component of the term of the eigenfunction is called vi, that it depends only on xi. The component of the eigenvalue will be xi0 times vi, okay? So if we put everything to the left, we obtain this strange result that xi minus xi0 times v must be equal to 0, okay? But on the other hand, you remember the eigenfunction is by definition non-zero, cannot be identically equal to 0, okay? Because this is the trivial solution and must be discarded, okay? But in order to have this product equal to 0, in which v is non-identically 0, we must have that the quantity in parentheses xi minus xi0, that of course is different from 0 for any value of xi that is different from xi0, okay? So the first parenthesis is identically different from 0 everywhere else but in one point. So vi must be 0 everywhere with the exception of the point xi0, okay? In the point xi0, the first parenthesis is 0 itself, okay? So we could say vi can take any value, but that would not be sufficient because this would make v still identically 0, but from a null interval, okay? So the only possibility for this equation to be solved is that v is a Dirac delta, okay? So you know that it is forbidden to consider d as a function, but if we do it for a second, we say delta is 0 everywhere, but in the point x10 where it is infinite, okay? So the solution of the eigenvalue problem for position is a delta function, is a Dirac delta. If we repeat this for the 3 components, we find that the global eigenfunction that we call f must be the product of the three deltas associated to the three components of the coordinates. So we write it in a short notation as a Dirac delta of R minus R0. Because you remember the eigenfunction is the product. Instead, the eigenvalue is the sum, and the eigenvalue is R0 equal to x10 I1 and so for the other two components, okay? So this is the outcome for the construction of the eigenvalue equation for position. Another example is the example of momentum, because also momentum is a vector. So the second example is that we see that momentum can be expressed as the sum of three blocks, okay? So the operator associated to this vector is the sum of the three operators, because we have to replace piece by piece. We replace to P1 minus JH bar derivative with respect to X1, and the same for P2 and the same for P3. So we have minus JH bar, and then we have a quantity between parentheses that is obviously the gradient operator, okay? Then we construct the eigenvalue equation for the momentum, and this eigenvalue equation will be minus JH bar gradient of f, we still call f the eigenfunction, equal to some constant that we call P0 times f. Again, since the original operator is the sum of blocks, then the problem is separable. Again, we call V the individual eigenfunction along each component. So the eigenvalue equation for each component will be minus JH bar V prime, that is the derivative of VI with respect to XI, equal to the constant Pi0 times Vi. The solution is obvious, is the exponential of JKI XI, in which Ki is momentum divided by H bar, okay? Of course, the equation is homogeneous, so it is defined apart from a multiplicative constant, and for convenience, we select the multiplicative constant as 1 over the square root of 2 pi, that is the one that appears in the Fourier transform. Later, we put all these blocks together. So the eigenvalue k will be the sum of the three, k1, I1 plus the others. And the eigenfunction will be the product. So it is 2 pi to the minus 3/2 times the exponential of jk dot r, okay? So these are two examples. Again, you observe that the eigenfunction for the position and the eigenfunction for the momentum operators are the Fourier transform of each other. We already noticed that, okay? And you may start now understanding why, because we have already met situations in which the coefficients of the expansion are the Fourier transform. So these relations connected to the Fourier transform are present in the theory. Sorry. In many cases, we do not have to deal with a single particle. We may easily find cases in which we have more than one particle in the system that you are considering, and that the particles interact with each other. The interaction is important because if the particles did not interact, we could consider each particle as a particle alone, so as a separate thing with 3 degrees of freedom. Okay, so when we consider many particles, we must always specify that the particles are interacting, so they form a system of particles. Let's continue to assume that the forces that are present in the system are conservative. Okay, so we can define a total energy of the system. The situation is more complicated, but only formally, because we may remember that a single particle is something that has 3 degrees of freedom. When we consider a system of many particles, we have many degrees of freedom, but the structure of the operations to be done does not change actually. Okay, so if we have a system of n interacting particles, okay, and we want to describe it with the language of quantum mechanics, we must introduce a wave function of the full system. So the wave function of the full system will depend, instead of depending on one position vector and time, it will depend on as many position vectors as necessary. So if there is a number of particles that is equal to some n, we shall have a wave function that depends on n vectors and position vectors, R1, R2, etc., up to Rn, and time. Okay? We assume again that the wave function is normalizable. So this more complicated wave function will still have the meaning of probability density. Okay? What we do is that we take the square modulus of the wave function at some instant of time, okay? And then we multiply this square modulus by the elementary volume associated to the first vector, so D3R1, then by the elementary volume of vector R2, and so up to Rn. And the meaning of this product is that it is the probability of simultaneously, that means at the instant t, localizing the first particle in the volume dR1, D3R1, and the second particle in the volume D3R2, and so and so. So it is simply an extension of the property of the wave function associated to a single particle. Okay? Now it is 11, so we stop for 10 minutes, and then we shall construct the theory for the system of m particles. Of course, it will be very similar to that of a single particle, so we shall not spend too long on it. Okay, so we shall continue in 10 minutes. Okay, so let's continue. We have introduced the concept of the wave function that describes a system of particles. And obviously, the procedure by which we define the Hamiltonian operator for a system of particles is identical to that used for the single particle. We still assume that the system is conservative, so we assume that there is a potential energy V that in this case depends not on one coordinate vector, on one position vector, but on the position vectors of all particles. So V depends on R1, R2, etc. up to Rn. Then we define the total energy of the system, and you can see it written on the left of the arrow. The total energy, that is the Hamiltonian function in classical mechanics, is the sum of the kinetic and potential energy. The kinetic energy, as usual, is the sum of the individual momenta squared divided by 2m for each particle. So in the sum from 1 to n, the index counts the particles. So pi squared is the square modulus of the momentum of particle of index I. And mi is the mass of this particle, because the particle may be different, so the masses must also be distinguished with an index. V is the potential energy that depends on the positions of all particles. At this point, we use the same recipe as before to form the quantum operator, the Hamiltonian. Each pi squared is replaced with the Laplacian times h minus h bar squared, because it is like pi is replaced by minus j h bar derivative. So when we square, as you remember, we obtain minus h bar squared Laplacian. I indicates the Laplacian with respect to the coordinates of particle number I. Okay. Now, is this Hamiltonian separable? In this form, it is not separable, because the kinetic part, of course, it is always separable because it is a sum of pieces. Each piece is associated with a single particle. So it is first separate. I'm speaking of the kinetic part. It is separable with respect to the particles. And then the Laplacian is separable with respect to the components, because it is the second derivative with respect to x1 plus the second derivative with respect to x2 and so on. So the kinetic part is always separable. Unfortunately, the potential energy is not. The potential energy is a function in which, since all particles interact with all other particles, okay, in the expression of the potential energy, we find all the coordinates mixed in a way that is, in general, non-separable, okay? However, it may happen that the potential energy is separable. You remember one case. One case is the case of the situation of a crystal in which the atoms are tightly bound to each other, you remember. So they may have displacements with respect to the equilibrium position that are so small that we can expand the potential energy up to second order, okay? We have treated this case in detail, and we have found that in that case there is a set of coordinates that we have called the normal coordinates, in which the problem is fully separable, okay? So if it happens that the Hamiltonian is fully separable, at least with respect to each individual particle, as you can see in the formula on top of this page, okay? This is good news because we can express the Hamiltonian as the sum of Hamiltonians associated to each particle individually. And you remember, when we have an operator of this type, then the eigenfunction is the product of the individual eigenfunctions, and the eigenvalue is the sum of the individual eigenvalues. So we can solve the problem particle by particle. This is, of course, extremely useful because it reduces the complexity of the problem enormously. And the complexity is even further reduced if the particles are identical to each other. For instance, if we have a system of electrons, as typically happens in semiconductors, okay? Because in that case, we may even be so lucky that eventually, since the separation provides a set of Schrödinger equations that are identical to each other, we just solve one single particle Schrödinger equation. So we have an enormous number of particles, but exploiting on one side the separability of the system, and on the other side the fact that the particles are identical, we find the solution of the single particle equation, that of course is much, much easier than solving the whole system altogether. And then we say the eigenvalues and the eigenfunction of the single particle Hamiltonian are representative of all particles. So they apply to all particles. These eigenvalues are the eigenvalues of each particle of the system, and these eigenfunctions are the eigenfunctions of each particle of the system. This is what is typically done in crystals, okay? And of course, the solution of the problem is made much easier by this separability property. We skip this part. And we now consider a different issue that is also very important. It may happen that two operators, A and B, have the same eigenfunctions. We already have considered one case of this type. You remember that a few slides ago we considered the solution for momentum. You remember that we found the functions of momentum in one dimension. They are the exponential of the type A, exponential of jkx. In three dimensions, they are exponential of jk dot r, okay? But earlier in the game, we solved the problem of the Schrödinger equation for the particle in free space to find the eigenvalues of energy and the eigenfunctions of energy. And if you remember, we have found that for a free particle, the eigenfunctions of energy are again the exponentials of jkx in one dimension, okay? So we notice that the Hamiltonian of the free particle and the momentum operator are two different operators, but they have the same eigenfunctions, okay? This is no surprise because you remember, for a free particle, if we know momentum, we take the square of momentum and divide by twice the mass, we obtain the energy because the total energy is equivalent for the free particle to the kinetic energy. So the information about momentum is equivalent to the information about energy. The converse is also true apart from the sign. If we know energy, we know the modulus of momentum. So for the free particle and for the corresponding Hamiltonian operator and for the momentum, we have a common set of eigenfunctions, okay? Knowing whether two operators have a common set of eigenfunctions or not is important. Why? Well, let's continue to consider the case of the free particle. You remember, if we measure momentum, we also find energy. Okay? That means that in this case, we do not have the problem that we had, for instance, with, remember, position and velocity when we had to measure the velocity of the bus with the tennis ball, okay? In that case, we observed that measuring one dynamic property perturbs another dynamic property, okay? So measuring position perturbs momentum, okay? In this case, measuring momentum does not perturb energy. We actually find both things with the same measurement. And the reason is that the eigenfunction is the same. The state of the particle happens to be the same for momentum and energy of the free particle. Okay? So for the free particle, measuring one of the two quantities does not perturb the measurement of the other dynamic quantities. So we may have fun for a free particle. We may continue to measure momentum and energy and momentum and energy, momentum and energy forever. We shall keep finding the same thing, okay, without perturbing each other. The reason is that the eigenfunction is the same. Is this sufficient? Well, no. It may be just by sheer luck that we have the same eigenfunction. So we must have the same eigenfunction no matter what the value of momentum or energy is. Okay? So we actually, in order to be sure that a measurement of one quantity does not perturb the measurement of another dynamical quantity, the two quantities must be associated to the same full set of eigenfunctions, okay? So the two operators possess the same complete set of eigenfunctions. If that happens, the measurements of the two quantities do not perturb each other. Okay, so they are compatible. So we have found by this short discussion that if two operators possess the same complete set of eigenfunctions, then they are compatible, meaning that the measurements of the two observables associated to the two operators are compatible. They do not perturb each other. So this provides us with a possible check in order to see whether there is a perturbation or not. We just solve the two equations. We look whether there is a common set of eigenfunctions of the two operators, okay? This is formally correct, but of course it is very inconvenient because for each operator we should be forced to find all the eigenfunctions just to check for the compatibility, okay? So is there an easy way out? Fortunately, there is an easy way out because there is a theorem that helps us. And the theorem is the following. If two operators, A and B, have a common complete set of eigenfunctions, then they commute. What is the meaning of commuting? Meaning is obvious that AB is equivalent to BA. So two operators commute when we can apply B first on a function and A second, or vice versa, we can apply A first and B second, and the result is just the same for any function that we select. Okay? Why is this theorem very useful? Because checking for commutativity of two operators is much easier than checking for the presence of a common set of eigenfunctions. Okay, we do not have to solve anything. We simply check whether the two operators commute. But now we must prove the theorem. Okay, so let's start by taking two operators A and B having a common complete set of eigenfunctions. That means that if V sub n is an eigenfunction of A, it is also an eigenfunction of B. Okay, for every n. As usual, we consider for simplicity a discrete spectrum. Okay. So let's take any eigenfunction Vn and then apply B first and A second. So we have A, B, Vn. Vn is an eigenfunction of B, so B applied onto Vn gives the eigenvalue Bn times Vn. The eigenvalue is a number, so we can place it to the left. We have Bna over Vn. But Vn is also an eigenfunction of A, so this is equal to Bn, An, Vn. Then we start this procedure over again by letting A first and B second. So BAVN is equal to BANVN. The eigenvalue AN goes out, ANBVN, ANBNVN. So if A and B have an eigenvalue, an eigenfunction in common, then they commute over that eigenfunction Vn. So it is not finished because we have demonstrated commutativity only with respect to the single eigenfunction, okay? However, the set of eigenfunctions is complete. So we can take any function f now. We calculate ABF. Thanks to the completeness of the Vn, we can expand f into the Vn. So AB applies onto the sum of Fn is coefficient, of course, of the expansion. Fn Vn. The sum commutes, so we can take it out. The coefficients Fn are numbers, so we can take V out. Then we have AB applied onto the single eigenfunction, but we know from the previous demonstration that B and A commute, so we can write it BA Vn. Then we can take it out again, and we have BA over F. So we have demonstrated that if A and B have a common set of eigenfunctions, then they commute. Now we have to demonstrate the converse, okay? So if A and B commute, then they have a common complete set of eigenfunctions. This is easy if the eigenfunctions are, if the eigenvalues are simple, okay? So we assume for the moment that they are simple, okay? So we now start with the hypothesis that A and B commute, and we apply this property of them on any eigenfunction Vn of A. So in this case, Vn is an eigenfunction only of A, because we do not know yet whether the two operators have a common set of eigenfunctions. But A over Vn gives An times Vn, because Vn is an eigenfunction of A, okay? Now, we apply AB over Vn. Then we apply commutativity, so we place B to the left. A remains on the right and gives us the eigenvalue An times Vn, okay? And then we place, again, B inside. So we take the eigenvalue An to the left. And we define a new function that we call Gn equal to the application of B to Vn. So we find that if Vn is an eigenfunction of A, also Gn is an eigenfunction of A, because this is given by the procedure that we have just found. You see the equation, A followed by B over Vn, okay, if it's like A over Gn. And the right-hand side is An times B over Vn, which is An times Gn. So Gn is another eigenfunction of A, okay? That belongs to the same eigenvalue An. Now we have to distinguish between two cases. That is, if the eigenvalue An is not degenerate, that means that to the eigenvalue An, there corresponds one and only one eigenfunction. But apparently we have two eigenfunctions here, because one is Vn and the other is Gn. Okay, so Vn and Gn must be the same function apart from a constant, because the problem is homogeneous. Okay, so we may let Gn is equal to a constant that we call Bn times Vn, okay? then we remember that the definition of Gn is the operator B over Vn, and we find that Vn is also an eigenfunction of B, because it is operator B over Vn equal to the constant Bn times Vn. Okay? So if there is a non-degenerate case, the the theorem is immediate. If there is degeneracy, the property is still valid, but the demonstration is much, much longer and tedious, so we don't do it, okay? In any case, we have demonstrated that if and only if two operators A and B commute, then they have a common complete set of eigenfunctions. So commutativity is easily checked. So if we want to check whether the measurements of two dynamical properties are compatible, we check the commutativity of the two operators, and that's it. If they commute, then we can measure one property without interfering with the other property, without influencing the value of the other property. If the two operators do not commute, then we cannot. Like it happens, as you remember, with the position and momentum. We now introduce another very important concept of quantum mechanics, and this concept is the so-called expectation value. The name is fancy, but the physical meaning is immediate, okay? So again, we start with some Hermitian operator A associated to an observable A, and consider a normalizable wave function. So the norm of the wave function is equal to 1, okay? Then by definition, the expectation value of the observable is the scalar product that you see in the definition. So we apply A to the wave function, then we multiply to the left by the conjugate of the wave function, and then integrate over the space, okay? Since A is Hermitian, we can indicate this operation with 2 bars, okay? Now, this is a purely abstract definition. The definition applies in this form because the norm of the wave function is equal to 1. If the norm of the wave function is not equal to 1, we should divide the scalar product psi A psi by the norm, okay? But we always assume in this context that the wave function is normalized. Now we can easily prove that the expectation value is equal to the average of the eigenvalues of the operator, okay? In this way, we actually introduce some statistics, as we shall see later in the operations that we do with the wave function, okay? So the first step is to prove that the expectation value is the average value of the eigenvalues of the operator. As usual, we consider the discrete case, take the expansion of the wave function. So we have the wave function as a sum of coefficients Cn times Vn. in which the coefficients, as you remember, are the scalar product of the terms of the expansion, the eigenfunctions times the wave function. Okay. Due to normalization, you also remember that the probability to find the eigenvalue of index n is the square modulus of Cn. Okay. So obviously, if we want to calculate the average value of the eigenvalues using the standard procedure of statistics, what should we do? We take each eigenvalue an. We multiply the eigenvalue by its own probability and we sum up, okay? In principle, we should divide by the sum of the Cn squared, but this is equal to 1, so we don't do it, okay? So the sum of Cn squared times An is the average value of the eigenvalues by definition of statistics. There is no quantum mechanics here. It is just a set of numbers. Each number has its own probability and we take the average weighted by this probability. Then we play some trick, okay, because we write Cn squared in a fancy way. We write Cn squared as Cn times Cn star. And Cn star is also written, as you see in the parentheses, as the sum of all possible Cm stars times the Kronecker delta of Mn. Okay, so in the parentheses, the delta kills everything but Cn star. So this is the fancy way of writing Cn star. But then we remember that the eigenfunctions of the operator are mutually orthogonal. So the delta can be written as the scalar product of Vm times Vn because they are orthogonal. Okay. Then we mixed up a little bit the terms. So we bring all the numerical parameters inside the scalar product. So on the left we have sum of CMVM. On the right we have sum of Cn ANVN. On the other hand, ANVN is like the operator operating on Vn. The operator is Hermitian, so we can bring it in the middle of the product. And we are left that we have on the left psi, because we have the expansion of psi, and on the right we have the expansion of psi again. So this demonstrates that the definition of the expectation value that we started from is exactly the average value of the eigenvalues. And the last line repeats the definition of average using the symbol P instead of using the square modulus of Cn, and using also the denominators, but the denominators are equal to 1 because of the normalization. Okay, so we have introduced an average of the eigenvalues. We may still play a little bit on these averages because we can extend the ideas to other possible averages that are important in statistics. You may have heard in some other occasions that we have the variance, the standard deviation, and other concepts of statistics. Okay, so we now calculate also these quantities in this context. Of course, we can repeat the analysis in the continuous case, okay? So we use the integrals and the Dirac delta instead of the sums, okay? But let's go back to the discrete spectrum. We may also decide to calculate the average of the squared eigenvalues of the eigenvalues to the third power, whatever we like. We can take the average of any power. So for instance, if we want to deal with a square, we remember that an operator squared is just an operator written 2 times. So if we apply an operator squared to the eigenvalue, to the eigenfunction of the operator, we have A followed by A operating on Vn. The quantity in parentheses is just the eigenvalue times the eigenfunction. We bring the eigenvalue to the left. We have again A operating on Vn. So finally, we have the squared eigenvalue times the eigenfunction. Okay, so this gives us the clue as for the calculation of the average of the squared eigenvalues, because we repeat the definition of the expectation using A squared instead of A. Okay, so this quantity, when written in the explicit form of the integral, is like psi star followed by A operating on psi. But A is Hermitian. So the first A can be brought to the left. So we obtain A psi scalar product A psi, which is obviously the square modulus of A psi. So it is something that is non-negative. Okay, so this quantity is strictly non-negative. Okay. Then we can calculate the variance. You remember what is the variance in statistics. Okay, the variance in statistics is calculated like this. You take the quantity of which you want to calculate the averages, that is the observable A. Then you take the observable and you subtract the average. Okay. Then you calculate the square of this quantity. So you obtain something that is by construction non-negative. Okay. If you perform the calculation, you obtain A squared minus 2 the average of A plus the average of A squared. But you see immediately that there is another average around by construction, okay? So the average of A gets average and multiplies the average of A already averaged. So I have minus 2 average squared that cancels this one. So eventually you have that the variance, that is the quantity on the left-hand side, is something that is non-negative by construction. So it can be written as delta A squared because it is non-negative by construction. Okay. You see on passing that the average of the square is larger or equal than the square of the average because the left-hand side is non-negative. Okay. Then in statistics, you define the square root, the positive square root of the of the variance. You call it the standard deviation. So the standard deviation for which we use the symbol delta A, is the positive square root of the variance. Okay, so these concepts are concepts of statistics. In principle, they have nothing to do with quantum mechanics. However, in our case, what we do is that we are taking the averages of the eigenvalues that are properties of quantum mechanics, okay? So, for this reason, instead of using the general term average, we use the term expectation value of the operator, because we are considering the average of the eigenvalues. And instead of using the normal term standard deviation, in quantum mechanics, for the square root of the variance, we use the term uncertainty. Okay, so the term uncertainty indicates formally the positive square root of the variance in the quantum mechanical case. Okay, this term uncertainty is very unfortunate because it is a term that is also used in the classical theory of measurement, uncertainty of a measurement. Okay. So it pre-existed to quantum mechanics, okay? But then they started applying also to quantum mechanics, and this was a very unfortunate choice because it gives easy access to philosophers. Philosophers like to play on this term, okay, to philosophize on quantum mechanics, which is really unfortunate. It is just a technical name for a very precise quantity, that is the positive square root of the standard deviation of the eigenvalues of an operator, okay? There are theorems that correlate the standard deviation of the eigenvalues to some other property of operators, and in particular, we find interesting outcomes if we consider operators that do not commute. You remember, if two operators commute, then they have a common set of eigenfunctions, and the measurements of the observables corresponding to these two operators do not interfere with each other. They are simultaneously observable, okay? But there are many situations in which we find operators that do not commute, okay? So we have to elaborate a little bit more on this. We shall start in the last few minutes that are left, and we shall continue on Thursday. We must define the commutator of two operators. So here, for some reason that will be clear immediately, instead of using the symbol A and B, we are using the symbol A0 and B0, okay, but nothing changes. So if you have two operators, A0 and B0, you define the commutator of them and use the symbol C0 for the commutator, as you see in this line. The commutator C0 is such that if you multiply it by J, you find A0 B0 minus B0 A0, okay? Obviously, this definition is fully general, so it incorporates also the situations in which the two operators commute. If they commute, the commutator is just 0, because you remember, if two operators commute, AB is equal to BA. That is, applying AB to any function is equivalent to applying BA to any function, okay? So if they commute, the commutator is 0. If they do not commute, the commutator is non-zero. So C0 is some other operator, okay? Why do we use the coefficient J in the definition? The reason is easy. With this definition, with the J, if A0 and B0 are Hermitian, then C0 will also be Hermitian, okay? So we now shall consider the case of two Hermitian operators, A0 and B0, or more generally A and B, that do not commute, so they do have a non-zero commutator, and we shall try to find, if any, some relation between the standard deviation of A and the standard deviation of B, okay, over the same wave function. Okay, so we have no time to complete the analysis, but we simply introduce some definitions. Okay, so we start with an operator A. Then we simply define A0 as A minus the expectation value. Okay, so just to get rid of some constant. Okay, so actually the goal is to prove a property for operators A and B, but we shall use A0 and B0 as auxiliary operators just because it is easier. So A0 is A minus the expectation, and B0 is B minus the expectation. Of course, the expectations are constant, okay? So if A is Hermitian, also A0 is Hermitian, and if B is Hermitian, also B0 is Hermitian. Then we take the wave function. Of course, the wave function that we are considering in this analysis is the same for both operators. And we apply A0 onto the wave function, and the result will be called F. And then we apply B0 onto the wave function, the result will be called G, okay? So F and G in general are some complex functions obtained by this operation. Then we construct another function, that we call sigma. Sigma is, by definition, F plus J lambda G, in which lambda is any real parameter. Okay? So we construct a new function sigma. Okay? That is a linear combination of F and G. Okay? So sigma is another complex function. Okay? Obviously, the square norm of this complex function is non-negative. It could be 0, okay, but it is non-negative in any case, okay? So sigma scalar itself is non-negative, okay? Then we shall see what happens when we replace sigma with the expression used above, that is F plus J lambda G, okay? We shall see interesting properties, because after this replacement, of course, the scalar product must stay non-negative, okay? So this property is still valid after the replacement. We stop here and we shall finish this analysis on Thursday.